typical data science endeavor starts with the domain expert coming up with a business problem to solve using some data repositories he or she has access to. Then a data scientist proposes an analytical problem that, if solved, could produce predictions that would help understand and overcome the problem. She or he would then confirm with the domain expert that solving this analytical problem would in turn solve the original business problem. The process can repeat multiple times before a business problem can be completely defined analytically, and is usually carried out before any of the modeling or processing work is even started. But when we observed how data scientists define prediction problems, we noticed a pattern that could be standardized. First, they pick a time-varying column from the database, then they segment the data, apply a series of transformations, and then aggregate and generate an outcome called a label that one could attempt to predict using prior data. Given this process, the next step is to ask what sorts of functions to use. By observing a number of different prediction problems defined across a variety of data sets and a variety of domains, we started to define a space of operations and rules to combine them in sequence. So we defined three types of operations: row operations, column aggregation operations, and column transformation operations. Row operations take an entire row and produce a row with new values. Column aggregation operations take an entire column or set of multiple columns and produce a single value. Column transformation operations take an entire column or set of columns and produce a new column. So let's take an example. Consider a weekly sales column in a database. A user wants to predict whether there would be a spike in sales, where a spike is defined as the point when the difference in sales values between two consecutive time periods is greater than some threshold. In order to generate the labels indicating spikes in the data, the user will apply a diff operation to the sales column. Diff is a column transformation operation. The user then applies a greater than, or GT, row operation to the output rows, and finally a column aggregation operation called any, which checks if any of the values in the time period are equal to 1, as opposed to 0. This prediction problem formulation can be described as the sequence diff, GT, any. So we can build a number of these prediction problems by chaining together an arbitrary number of transformation and row operations, always ending with an aggregation operation. We assembled a list of functions for the three different kinds of operations. Armed with this very simple space, we can define hundreds, if not thousands, of prediction problems for any given dataset. Now, given a prediction problem definition, in other words, the definition of some outcome we want to predict, we are able to solve it end-to-end by automatically segmenting the data into parts used for learning and parts used for computing the outcome, featurizing the learning segments using an algorithm called deep feature synthesis, and automatically producing the outcome labels using the sequence of operations in the definition. Using all of these steps leaves us with data in a machine learning ready format, which we can then use to learn a machine learning model and produce an estimate of how accurately we can predict the outcome. To demonstrate, we took a public dataset describing Walmart sales data to find 235 prediction problems, and for each problem went through these end-to-end steps. We produced predictive accuracy scores for each without any human intervention. So what can this enable? This allows us to flip the conversation. Now a business expert can come and plug in data into the system. The system can come back and present results for many different prediction problems, one after another, to all of the stakeholders involved, without needing humans to intervene at any step along the way.